Welcome again. Today we continue with our course Computer System Architecture. In the last video, I started a revision of the material presented in Chapter 1. I already told you that the first 3 chapters in Morris Mano are a comprehensive revision of the digital design course. Digital logic circuits are classified into combinational and sequential logic circuits. In a combinational logic circuit, any of the outputs is function only of the inputs or sum of the inputs. While in a sequential logic circuit, any of the outputs is function of the inputs and the present state, since we have a feedback in the circuit and memory elements. Examples of combinational logic circuits are the group of adders, subtractors, code conversion circuits, multiplexers, demultiplexers, decoders, encoders, read-only memories, etc. If we need to store data, then the type of the circuit should be sequential, since combinational circuits are not capable of storing data. An example of a combinational logic circuit is half adder, used to add 2 bits together and produces their sum and carry. The sum here is 0, 1, 1, 0, and the carry 0, 0, 0, 1. So the sum is not xy or x not y, which is x exclusive or y, and the carry equals xy. And this is the circuit diagram for the half adder. Full adder is used to add 3 bits and outputs their sum and carry. This is the truth table for the full adder, and you know that the sum is exclusive or x or y or z, and the expression for the carry is xy or xz or yz. And from this expression, we can obtain the expression as in this form in order to implement the full adder using 2 half adders. Here is the logic diagram, circuit diagram for the full adder, and here is the block diagram. Here the full adder is implemented using 2 half adders. This is the first half adder, and this is the second half adder, and we need external OR gate in order to generate the carry. The basic sequential circuit is the flip-flop. The flip-flop is capable of storing 1 binary bit. There are several types of flip-flops: SR, D, JK, T, and others. All flip-flops operate with only positive or negative clock transitions, and therefore they are called edge-sensitive, unlike latches, which are level-sensitive. This is the circuit diagram for the SR flip-flop implemented using NOR gates, and here we have the graphic symbol for the clocked SR flip-flop. And this is the characteristic table for the SR flip-flop. As you see, in 0, 0, we have store, Q of t plus 1 equals Q of t. In 0, 1, reset. In 1, 0, set. And in 1, 1, undefined state. And this is one disadvantage of the SR flip-flop. This is the state table for the SR flip-flop. On 0, 0, we have store. On 0, 1, reset. On 1, 0, set. And in 1, 1, undefined. We can implement the SR flip-flop using NAND gates. In this case, the 0, 0 will be undefined state and the 1, 1 store state. From the characteristic table, we can obtain the characteristic equation for the SR flip-flop. Q of t plus 1 equals S or not R Q of t. Next, D flip-flops This is the graphic symbol for the D flip-flop. We have only one input, and this is the circuit diagram for the clocked D flip-flop. D in its normal form is applied to the first AND gate, and in its complement form to the second AND gate. So if D is 0, we'll have here 0, 1, which is the reset state. So the next state will be 0. And if D1, we'll have here 1 and here 0, which is the set state. In this case, Q of T plus 1 equals to 1. From the state table, you can see that Q of T plus 1 equals D, which means that D flip-flop always hold the information available on data input. The bit applied to the input is stored in the flip-flop. Next, JK flip-flops. JK is the modified version of SR flip-flop. The only difference that we have a feedback here and a feedback from here to here. This is the graphic symbol for the JK flip-flop. Here the characteristic table for JK flip-flop. On 0, 0, we have store. On 0, 1, reset. On 1, 0, set. And on 1, 1, store complement. If the present state is 0, the next state will be 1. And if the present state is 1, the next state will be 0. So here we have int and defined state like in SR flip-flop. From the characteristic table, it's easy to derive the state table for the JK flip-flop. On 0, 0, we have store. On 0, 1, reset. On 1, 0, set. And on 1, 1, store complement. And from the characteristic table, also, we can find the characteristic equation for the JK flip-flop, which is Q of T plus 1 equals J not Q of T or not K Q of T. Next, T flip-flops. T flip-flop is the simplified version of JK flip-flop. It's obtained by connecting the same input T here to both inputs of JK. Here is the graphic symbol for the T flip-flop, and here is the circuit diagram for the flip-flop. As you see here, if T is 0, then we'll have here 0, 0, store. Here if T is 0, the next state is a store. And if we have here 1, then we'll have here 1, 1, store complement. Here is the case. 1, here, store complement. The state equation for the T flip-flop is here, not T, Q of T, or T, not Q of T, or Q of T plus 1 equals T exclusive or Q of T. Again, regarding the edge-triggered flip-flops, I mentioned that all flip-flops are triggered on the positive or negative edge of the signal. Here we have a positive edge-triggered D flip-flop, and here a negative edge-triggered D flip-flop. In the positive edge flip-flop, transitions occur here, and on the negative, transitions occur here. And here we haven't any change, and here we haven't any change. Next, excitation tables. The characteristic tables of flip-flops specify the next state when the inputs and the present state are known. During the design, we usually know the present state and the next state. So we need to find out the flip-flop inputs that will cause the required transition. In the characteristic table, we have the inputs, present state or states, and we need to find the next state. However, in the excitation table, we know the present state and the next state, and we need to find the flip-flop inputs that cause this transition. This is the difference between the characteristic table and the excitation table. For example, the excitation table for the JK flip-flop. Here we have Q of t plus 1, and we need to find JK. If the present state is 0 and the next state is 0, this can happen if JK 00 store state or 01 reset state. So we'll have here 0 and K do not care. Now from 0 to 1, this is the set state 1, 0 or store complement 1, 1. So J1 and Kx. In the same manner, from 1 to 0, this is the reset state or store complement, which means X1. And from 1 to 1, this is the store state 0, 0 or the set state 1, 0, which means X0. So this is the excitation table for the JK flip-flop. For example, for the T flip-flop, if Q of T is 0 and the next state is 0, this means that we have 0, and here 1 and 1, here we have 0, store state. In these two cases, T is equals to 1. And this is the excitation table for the T flip-flop. We need to know the excitation table and the design procedure of the sequential circuit. Here we have the excitation tables for the SR flip-flop, D flip-flop. For the D, it's easy. D equals to Q of T plus 1. J, K flip-flop, and T flip-flop. Sequential circuits are classified into synchronous. In this case, the clock pulse is applied to all flip-flops, and asynchronous, the clock pulse is applied usually to the first flip-flop, and other flip-flops are triggered internally. This is the block diagram of a clock synchronous sequential circuit. We have the combinational part and the flip-flop with a feedback to the circuit. Regarding the analysis procedure of a sequential circuit, you know, in the analysis procedure, we usually have the circuit, and we need to derive the state diagram, the characteristic table, the characteristic equations, and if possible, the description of the circuit. In order to do that, here we find DA, here's the A flip-flop, and the B flip-flop. As you see, DA equals to X ANDed with A or X ANDed with B. DB equals not A, here, ANDed with X, here is DB. And the output Y equals A, here, A, not X, here A, not X, and here not X, and it would be B, not X. So the output Y equals A not X, B not X. Now having these equations, we can derive the characteristic table, state diagram. Here are the equations. Since we have two states AB and one input X, we list all the possible states here, 0, 0, 0 to 1, 1, 1, and the next state for the flip-flop A equals here, in this case, AX or BX, and B, not A, X, for the next state, 0, 0, 1, A, AX, BX, again 0. However, here, not A, 0, and with X, 1, 1. And for example, here, 1, 1, 1, A equals AX, BX, 1, and B equals not A, x, 0. In the same manner, we find y from this expression, and here is y. And from the state table for the circuit, we can now derive the state diagram. We have 4 states, 0, 0, 0, 1, 1, 0, 1, 1. On 0, 0, there are 2 states. If x 0, then the next state is 0, 0. Here we have it. And the output is 0. Here we have it. On 0, 0, if the input x is 1, then the next state is 0, 1. Here. And the output is 0. Here we have it. On the state 0, 1, here 0, 1. If x is 0, then the next state is 0, 0. Here. And the output is 1. Input x 0 and the output is 1. However, if the input is 1, then the next state is 1, 1 here. And the output is 0. And I think it's easy for you to continue and derive the complete state diagram for the given sequential circuit. Regarding the design procedure of a sequential circuit, the input is the state diagram or the state table, and we need to design the circuit or obtain the circuit diagram. For example, to design a 2-bit binary counter that counts from 0, 0 to 0, 1, 1, 0, and 1, 1. X here is the count. So if X is 0, then always will remain the same state, no count. However, if X is 1, if the state is 0, 0, then the next count is 0, 1. And if the current count is 0, 1, the next count is 1, 0. And the next count is 1, 1, and repeat. This is the state diagram for a 2-bit binary counter. Here you can see that we have 4 states and no state reduction is possible, so we need 2 flip-flops. One input, which is the count, or X in this case, and suppose that we need to design the circuit using the JK flip-flop. Then we can draw the first skeleton of the circuit. We have here 2 flip-flops, AB, with the clock pulse applied to the flip-flops, the external input X or count, and here the circuit is of type more, since output values are determined only by the current state of the circuit. In melee circuits, output values are determined by both the state and the current inputs. So this circuit is of type more. Now we need to find JA, KA, JB, KB. To derive the excitation table for the binary counter, here if the flip-flop 0, 0 and the input X is 0, the next state is 0, 0. If 1, the next state is 0, 1. On the state 0, 1, if the input is 0, the next state is 0, 1. However, if the input X is 1, the next state is 1, 0. Now we need to find GA, KA, JB, KB. Here we have the excitation table for the JK flip-flop, so we needed to find out these inputs. For example, for the A flip-flop from 0 to 0, here we have 0x. For the B flip-flop from 0 to 0, again 0x. The next state from 0 to 0, again 0x. From 0 to 1, here we have 1x. The next from 0 to 0, again 0x. And from 1 to 1, x0. Next from 0 to 1, here. From 0 to 1, here. we have 1x, and B from 1 to 0, here, from 1 to 0, x1. Next, A from 1 to 1, x0, and B from 0 to 0, 0x. Next, A from 1 to 1, here, x0, and B from 0 to 1, 1x. Next, A from 1 to 1, here, x0, and B from 1 to 1, again, x0. And the last row, A from 1 to 0, from 1 to 0, we have x1, and B from 1 to 0, x1. Now we need to find the expressions for JA, KA, JB, KB. For example, for JA, we have here 0, 0, 0, 1, 0, 0, 0, 1, x, 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 x. So JA equals, as you see, bx. KA equals x, 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 0, 0, 0, 1. Again, KA equals here bx. JB equals 0, 0, 1, x, x, 0, 1, x, x. Here we have JB equals x. And KB xx 0, 1, xx 0, 1. Again, KB equals x. Now having these expressions, we can proceed to draw the circuit diagram. Now having these equations for the flip-flop inputs, we can draw the logic diagram of a 2-bit binary counter. Both JA and KA equals BX, here B ANDed with X, here we have BX, and JB and KB equals to X. Suppose that the initial count is 0, 0, and here we have 1. So here we'll have 1, 1, and here, since we have here 0, we'll have 0. 0 store, and here 1, 1, store complement. Next count. If the current count is 0, 1 here, and we have next count 1, then we'll have here 1, 1, and we'll have here 1, 1 complement, here 1, and here 1, 1 store complement. So next count will be 1, 0. And on 1, 0, if we have a next count, so here we'll have 1, 1, and here 0. 0 meaning store, 1, and here store complement 1. So we count from 0, 0, 0, 1, 1, 0, 1, 1, and repeat. This is chapter 1 in Morris Mano, and it was a comprehensive revision for some topics from the digital design course. For today, that's all. Thank you.